Hi everyone, Warren Su from SQUID3 Space. Hope everyone's having a great day so far. We're developing thermal solutions to help satellite manufacturers integrate the thermal control systems 30 times faster. And for context, every satellite needs a thermal control system because space is very extreme temperatures. This is my co-founder, Dustin. He's a former satellite integration engineer for a small NASA mission that went to the moon. And well, this is him spending weeks meticulously crafting and applying thermal control tapes onto the satellite exterior. And according to him, his team had to follow a legacy workflow developed by NASA back in the 80s. And this exact combination of outdated technology and process is a common pain point that many space companies highlighted during our customer discovery. So we learned that existing thermal solutions available on the market are outdated. They rely on materials with fixed properties, which make the thermal profile of the satellite mission specific. And as a result, satellite manufacturers waste 3 to 6 months to develop a different thermal profile for each new mission. And this has been okay for the past 30 years, but we see it is no longer the case today because the US Space Force aims to establish a capability so-called tactically responsive space by 2026. Our defense customers want to integrate and launch their satellites in just under 60 hours. And this is a drastic shift from the years of development it traditionally takes. So what SQUID3 is bringing to the market is a solution called ASTRID that streamlines the thermal development cycle by 30 times. ASTRID is a smart material that is enabled by e-ink and have dynamic properties that can be defined and configured through software. And it's designed to transform satellite exterior into these programmable surfaces that can match different mission environments, whether it's hot or cold, instantly. And the impact we're making here is reducing that thermal development cycle from the average 3 to 6 months today down to a timeline of hours or days. So far, we have received interest from Northrop Grumman and several commercial space companies, which are contractors of the US Space Force. And our solution has also received positive reviews from experts at the Air Force Research Lab, which is why we've recently been awarded a $75K SBIR Phase 1 by them. And finally, this is our team. My team has 60 years of combined experience in space technology R&D. I am a former satellite control operator. My COO built satellites that went to the moon, and my CTO is worked as a materials engineer at NASA JPL. Thank you, Anna. Happy to answer some questions.
In the full price of constructing a satellite, what percentage of that cost is the thermal control system? I'm trying to figure out, how material is it to the overall cost of the satellite?
It's usually between 6% or so. And so for a small satellite, we're talking about, $2 to $3 million for the whole satellite. And so the thermal control system gets a budget of around 50 to 80K.
What's the current annual spend on thermal tape solutions for the satellite industry as a whole?
Market size wise, so this is the thermal control market has it's currently $600 million annual market, and it's expected to grow with more satellites launching each year. By 2030, it's expected to double.
How many major players are there in that market today?
Very few, and so actually, it's the suppliers of the supply of thermal control tapes today are locked up inside a few suppliers domestically, and that's actually one of the pain points that some of our customers have told us during interview is they wish to see more diversity in this market.
Have you been able to test your product yet in any extreme conditions, such as flying it in space yet, or even here on Earth?
Yeah, so give you a quick overview of our roadmap right now. So we're currently, we just finished our MVP development last quarter. And at the moment, we are performing the environmental testing. Then some of the specific tests we're doing include thermal vacuum, UV radiation, and we expect to conclude the environmental testing by around July to August timeframe. And our end goal, kind of long-term goal here, is to test fly our technology on the International Space Station by Q4 2025. And so kind of what we need to get there is capital. So we are actually raising about 200K, hopefully by July or August, so that we can to fund the fabrication of the hardware and the experimental unit that we're gonna send up to space.
Yeah, what do you think you need to show your customers to be competitive with the existing solutions? Is it on the quality or on the price?
So we are, we have four letter support signed by these companies, and they're definitely interested in our solution, but they like to see more test data. And so we're pretty confident that because we just recently received major funding in the past month, and so we expect to have test data on our hands that we can share with these customers hopefully by end of next month, and we'll be delivering small scale samples to them for them to evaluate our solution. And of course, for them to be convinced to purchase our materials in large quantities, we need to test fly it in space. So that we're aiming at kind of hopefully commercially available around Q1 starting 2026. Yeah.
Just out of curiosity, are there different use cases for your product? It seems like it's very versatile.
So one of the common questions we get from the investors is there terrestrial application? And that is definitely an area that we want to explore. We're trying to explore the market of greenhouse farms, specifically on providing smarter energy saving window solution for these greenhouse farms. And I know the board panel here is all in clean tech, so be interested in connecting more after this to see if there's any insights. Yeah.
Do you have anticipated production costs for what you think the cost of manufacturing is, and then what you think your margin is going to look like?
Yeah, so we're manufacturing this. So we're taking it to the contract manufacturing approach at the moment. So we price around, to give you an estimate for a small satellite, the whole solution will cost less than $50,000. For a large satellite, it's gonna be around $150,000. And I would say we are 5 times cheaper than our closest competitor. And the profit margin kind of varies depend on, of course, the mission lifetime and also which orbit it's going. So for a low Earth orbit mission where you're expected to operate for 5 years, we're gonna have profit margin of around 50%, and then charge higher for any missions that's going to more extreme environments, like higher orbits or maybe the moon.
What's the testing timeline with the customers that you were saying, some of them that were evaluating this product? What have you found is the timeline for them to adopt this type of technology versus the existing that they have in place?
So at the moment, none of our customers have any samples, but we're ready to deliver them starting at closer to the end of next month. And we believe the result for having our customers having hands-on getting the feel of our material is that can hopefully convert our letter of support into letter of intents. And at the moment, it's we have a SBIR phase 1 with the U.S. Space Force. So a lot of our customers who have signed the letter of support are also working with the U.S. Space Force. So with the end of the phase 1, we expect to come up with kind of a way to for our defense customers to adopt our solution onto their satellite. And by the end of the year, we'll be applying to basically a SBIR phase 2, and that's when we'll be actually most likely selecting a major prime contractor that builds satellites for U.S. Space Force or the defense community, and work with them to do a demonstration mission.
It seems to me that one of the big challenges you may face in commercialization is that the upside for a satellite manufacturer to adopt this is they can save a percent or a couple percent of cost. But the downside is that their satellite melts in space or whatever. So it's like a big downside risk for a relatively small upside. And yet it seems like it's going to cost a lot to actually prove this. My question is, and you showed on your timeline that you're going to have to actually send tests up into space and stuff. So do you have a sense of what kind of the cumulative cost is going to be for you to actually prove this to the level where the customers, the manufacturers, are going to accept the product? We talking $5 million, 10? What do you think?
$500,000.
Okay, so you can send test materials up into space.
Yeah,
within that 500,000?
We can complete that technology roadmap, saw earlier, with around $500,000.
Okay.
All right. Thank you so much.